Next speaker is Grazyna Horbaczewska, who speaks on permutations preserving density.
Okay. So first of all, I'd like to thank you for invitation to attend this seminar. It's really an honor to have an opportunity to give here a talk. Our group in Łódź, me and Sebastian Lindner and Władysław Wilczyński, we are not specialists on number theory. We have just noticed some facts, trying to solve a problem from the Scottish book. Thinking about this was very interesting for us. Of course, it would be much nicer to find a solution. But at the moment, I can present here only a kind of survey on this topic, our attempt, our attitude to this, some examples. So let's start. Okay, so the problem which was posed by Ulam in the Scottish book was formulated as follows. It was the task to find all the permutations of the sequence of natural integers which have the property that if nk is an arbitrary sequence of integers with a given density alpha, then after this permutation, it has also a density alpha in the set of all integers. So that was the formulation from the Scottish book, exact translation of this formulation, yeah? Okay, so we start from the basic definition. First of all, we would like to understand the notion of density. And it's an obvious notion for us, yeah? So when we think about a subset of natural numbers, about subset of positive integers, we check how much of the initial interval from 1 to n is covered by the set A, proportionally to the length of this interval. And when we compute the upper limit, we call it the upper density. When we are looking for the lower limit, it's a lower density. And if this limit exists, this common value is called the density of the set A. And we say that the set has an asymptotic density if it has this limit existing. So the upper and the lower limits are equal to each other. And I'm going to denote the family of set possessing this asymptotic density by AD. Okay, now think about preserving density. We can understand this in various ways. So, okay, something is invisible, but I think it's not a problem. It's written permutations here. So we are going to denote like that the group of all permutations of the positive integers. And we start with the family of permutations which preserve the upper and lower density. And so the upper density of the set before permutation is equal to the upper density of this set after the permutation, and here we have the same with lower densities. Okay. When we look at this very basic property that when we calculate the upper density of the set, it is equal to 1 minus the lower density of the complement, we can get rid of one of these equalities. Yes, because preserving one of these densities is followed by preserving another one. So we can get rid of one of them. I decided to write only this upper limit. Okay, and by very easy reasoning, we can justify that this family is a subgroup of automorphisms. Of course, there is no problem with composition. In this description, there is no problem also with inverse permutations, so we have a group here. Okay. We can also think about preserving density in the way I will show this, when we have the following conditions. So the family of sets having density is exactly the same as the family of images of these sets under our permutation. And treating a set by a permutation, we receive, it does not change the density of the set. Yeah, we receive the same. So again, it's easy to observe that we have here a subgroup. Again, it's not a problem. And we would like to think what happens if we get rid of this this equation, this equality, yeah?
Just one
So when we,
second. Excuse me?
yeah?
The way you've written it, as though it's a function with an argument, it doesn't actually mean that, right? There isn't a
Yeah,
variable.
it's
What?
just the notation of density, yeah?
Yes, okay. It's
The
the
group
G that's written.
preserving density, yeah. It maybe
Yes.
it should be here in the middle, but I wrote it like that. So
Okay.
when we get rid of this condition, we can denote this family by that. And now it comes to the reason I think I'm here, because in the beautiful paper written by Professor Nathanson and Professor Parikh, under this title, Density of Sets of Natural Numbers and the Levy Group, in Journal of Number Theory, there is a result which is as follows. So we can get rid of this equation and we receive this condition, and we receive the same family here. To be honest, in this paper, the result is even a little bit stronger, but for our purposes, I think this is crucial. So we can think about this like that. Okay, so have a look once again here. So we have a family of automorphisms preserving the upper density, and as a consequence, the lower density. And we have a family which preserves the density, which means really it preserves the family of sets possessing density. I'm going to use this notation, G of D, in the future, yeah? So it is obvious then this family is included in that, because when we have these both densities preserved, we have also this density preserved. So we can write like something like this. But we have observed that there exists a permutation which proves that that it's not the same family. And I would like to present here this example. Maybe I will switch my screen into something else to make it possible for me to draw for you something. Okay, so we see the same place. So let's think about this permutation. So first we make a division of the first order. I'm going to explain it later why I'm calling this first order. Yeah, it will be clear in a sec. So we make a division starting each, ending each set bi1 with the powers of 2. So we have sets ending at 1, 2, it's maybe something else. Oh no, it's okay, it's finishing at 2 to the power of 0. Here we have 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3, and so on. And then we would like to split each set from this group, starting from the set number 2, into the left and right part. And we divide them like having the same length, yeah? So when we have, for example, here the part, the set B consisting of numbers from 9 to 16, we divide it into two groups consisting of two equal parts when we think about the length, yeah? And now we consider a permutation which changes only the, take a pen, which changes only within this set bi1, it interchanges these groups, but can you see we don't change the order, yeah? So we exchange 5, 6 with 7, 8, we don't change the order, and here it's again the same. Okay, and now think about a set which consists only from the left parts, let's say, of each division. So we take as a set A, 3, then 5, 6, then this part, and so on. These left parts of each set from this division, yeah? So when we think about this set, the density, the upper density of this set is equal to 2/3. But after this permutation, this set changes into the set, maybe it will be visible here better. Yeah, it goes here, there. So it changes to the right parts of these intervals. So now thinking about the endings of these intervals, we receive the upper density of this transformed set equal to 1/2. So evidently this permutation is not in the family G. It does not preserve the upper density. Okay. So we can go to another slide. So now about this first order division. We made a division of the first order like that. It's just to remind you this. And then this dividing this into halves to define our permutation, we call this the second division. So we divide those sets which have more numbers than 1 into halves, and we enumerate them from the left once again. So here we have the set B0 from the second division, that's B1 from the second division, and so on. And we make next divisions at the same manner. So in the third division, we just divide these sets which has more elements than 1. And we make again this enumeration from left to the right, starting from B0, B03, and so on. So when we think about sets after the third division, we receive something like that. We have 8, it's visible here, I think. We have 8 sets with the cardinality 1. So yeah, ones, and the number of them is n, is 8. Then we have sets with the cardinality 2. They're visible here. Yeah. So, and we have 4 of these sets. Then we have 4 sets with the cardinality 4, and so on. So, and we repeat this procedure. So in the next step, I'm going to divide these sets containing more than 1 set into 2 sets. And here also we divide them into sets consisting of 2 elements. So we get more sets which are singletons, and then groups. So after nth division, we have 2 to the power of n sets containing 1 element, and then 2 to the power n minus 1 sets containing 2 elements, and the same number of sets containing 4 elements, and so on. So we receive here groups of sets. Each group consists of 2 to the power of n minus 1 sets, and each set in this group contains 2 to the power of k elements. And after each division, I make this notation that I enumerate from the left, them from the left. And then we manage to prove the following lemma. If a set has a density alpha, this is equivalent to the following condition, that for each order of division, so we make this division of each order and we compute this density. I mean, we check proportionally how much of the set A is covered by the set, comparing this with the cardinality of this set, this testing set. Yeah? And the existence of a density of the whole set A is equivalent to the existence of this limit for each order on the same level, it's equal to alpha. So I'd like to add a few words about this lemma in a sec, but first think about our permutation in the context of this conditions. So when we think about the set A and it has its density alpha, so using this lemma, we receive this condition that for every n, we have this limit equal to alpha. But if you remember my permutation, it changed only within the groups of the second order. So it was changing, it's like making here only the rearrangement of terms. So we have the same limits after the permutation. So it means after the permutation, we receive the same alpha here. And of course, we would like to check this also for the inverse, permutation, but it works also here. So we have this equation that the family of sets possessing density is not changed after the permutation. So we are in the family G of D. Yeah. Okay, now a few words about this lemma. So maybe I'm going to switch again my device into something else. I'd like to use this one. So the idea of the proof of this lemma is based on the following observation. If we have a density of the set, oh, sorry. Something happened with this. I'm lost. I don't know why it works like that. Maybe, okay. Maybe I should have a line. Sorry. If we have a density of the set equal to A, and we have theta belonging to the interval from 0 to 1, then the limit when we try to find the cardinality of the set A on the interval from theta n to n in comparison with the length of this interval, this is equal to A. And this lemma is very easy. Let's call it lemma. So this is very easy to justify this. So I'm not going to do this. Maybe it's needed here. And when we think about this like that, we have an interval which has a left end and the right end. We denote for this interval theta by theta of this interval the quotient, the left part divided by the left end divided by the right end. So it's something which corresponds to this, yeah. We can now think about our lemma. So it was like that. I would like to show the proof in one direction at the moment. So we have a density of the set equal to alpha and assume that there is something wrong. Assume there exists a division and there exists epsilon such that we can find a subsequence in our sequence of sets such that when we try to compare the cardinality of the set A on these chosen intervals of the nth order, and we compare this with cardinality of this set, we are far from our alpha. Yeah, we assume that there is something wrong, and we try to find a contradiction. But when we think about the sequence of n-ordered sets, so for the group of these sets having the same cardinality, Yes, because you remember that we have sets of the same cardinality, and these are groups of 2 to the power of n minus 1 sets of the same cardinality 2 to k. And previously we had the group of the same number of sets having the cardinality smaller by 1. Yeah, so these are these groups. So for these groups, theta can have only finite number of values. And this group of these possibilities for theta for each group is the same. So we have the final possibilities for getting theta for these sets. But we think here about an infinite sequence. So it means we have a common theta. Yeah, even maybe choosing some subsequence, we can assure that for every term from our sequence, the theta found for this special set is equal to the same number. I'm going to denote it by theta. Okay, so we are here. So we have a contradiction with this limit, yeah? Because we know now that the density, this limit should be equal to alpha. So we have something like that. Okay, and in the opposite direction, I don't want to present the whole proof in the opposite direction, but it's something like that, that we have here the long period of intervals on which the proportion on each of these intervals of the set A is the same. Then we have also something which finishes in the middle of this interval. But when we are far enough from the beginning, this interval is not important for us. So it means when we have this for this kind of division, but we have also the same situation for smaller divisions. Yes, we have also the same proportion here. So that's the power of this lemma, that we have this in each order of division, the same situation. So that's why we can receive that from having this limit for each order equal to the same number, we receive the density of this whole set equal to the exact number. If you wish, we can present this proof more detailedly later, but I think the general idea is enough here. Okay, so coming back to our talk. Okay, I have to make some. Okay, I cannot this with. I think it should work. Yeah. Okay, so we are here. We did this. We did also that. So we have here this lemma, and we know that we have permutation which shows that our families are not equal to each other. But to be honest, we are now still not in the situation when it was in Ulam's question, because he asked about the characterization of the permutations like that. So the permutation which preserves only, let's say, this family in one direction. Yeah, he asked about this situation that we consider a set having density, and then when we permute, we stay at the same family, and density is not changed here. And it occurred that it's not the same family as here, because this is not a group. And the example was delivered here by Koke in his paper Permutations, maybe not in English, des entières réparations de suite, okay, but he published it in Marseille. And I'm going to describe only main idea of this permutation, which shows that it is not a group. So this permutation is the permutation which belongs to this family, but the inverse one does not belong to this. Okay, so let's think for a while about
just
this.
Checking what this actually means is that this this permutation takes any set with a density, and produces a set with a density, but it also takes sets that don't have a density and turns them into sets with a density. It takes some sets that don't have a density and gives them a density, yes?
Yes,
Okay.
it's possible. Yes, it's possible. Yeah, maybe. Okay, maybe I will show this only, not using my pen, but only showing it like that, yeah? So we have the following permutation. We divide again natural numbers into groups, but these groups are now starting at powers of 2. So we start at 2 to the power 2, 2 to the power of 3, 2 to the power of k, yeah? And in each group, we make something like that we divide this group into 2 parts, and the left part is transformed into even numbers, and the right part is transformed into odd numbers. Yeah? Sebastian likes to describe this permutation as a Cinderella's stepmother permutation because she just mixed everything, yeah, here. And what is important here is to observe that we don't change anything inside the group, yeah? So we change with this permutation works only within a group. Okay, so this is enough to show that this permutation preserves density. Yeah, so for this reason, I'm not going to explain it detailedly, but it's the crucial point. But when we think about the permutation which goes back, and we think about the permutating back even numbers. So we are here, and when we think about even numbers, maybe it's more visible in this part. When we take only even numbers, it means we think about these blue arrows. So the density of these even numbers is, of course, a half. But when we go back using these permutations, inverse permutations, we are on the left part of these intervals. Yeah? And it works for each interval. So checking at these ends of the groups, we can see that this inverse permutation has a density a half, some kind of density. But when we are checking in the central point of each group, we can see that this is a 2/3. So the set of even numbers, which had the density a half, after coming back with this permutation to the previous situation, it lost density. Yeah, it's not a set having density when we come back. This beginnings of the blue arrows. So it works like that. So we now know that this is not a group. Okay, so we can prolong, I think. Okay. Now I'd like to think more detailedly about this Ulam's problem. So we can think about this a little bit more precisely. So we are going to think about preserving not density in any case, but we'd like to preserve a density for the special number which was chosen. Yeah, so we choose a number from 0 to 1, and we denote this family as the alpha, by as the alpha, the family of those permutations which satisfies the following conditions. Okay. And of course, an easy observation shows us that it's not important if we think about alpha or 1 minus alpha, because it gives the same family. It's obvious, it's this trick with the complement, yeah? But by Blumlinger and Obata in this paper from 1991, they observed when we have alpha from 0 to 1, any alpha, so it gives the whole family as D.
But that's strictly between 0 and 1, not including 0 and 1.
Not including, you revealed my secret. because it's my next thought. And it wasn't defined, yeah, this family, but I think you can guess what's that. So the same works, of course, for this family G. And as you said, we have the problem with 0 and 1. Okay, so it is repeating the previous situation, and now we have something like that there exists a permutation which proves that when we use 0, it's not the same. And firstly, I'm going to show an easy permutation, but I prefer to draw something. So maybe I will switch again my type of slides. Sorry for this, but it was easier for me to do that like that. Okay. Okay, so we are here now. So we have a permutation which we would like to show you a permutation which works like that. We have maybe I will draw it here. Okay, we have number 2, number 4, 6, and so on. So we have these even numbers, and they go into places where we have something which is equal to 1 modulo 10. So we have 11 somewhere here, and we exchange 11 with 2. Yeah. Then we exchange 4 with 21. So it goes like that, and so on. So you can see that other n are untouched by this permutation. Okay, and when we think about this given set, the set of even numbers, we can see that at the beginning it had a density half, and it was transported into the numbers which are equal to 1 modulo 10. So after this permutation, we receive here a density 1 over 10. So definitely this permutation does not preserve density. But when we think about a set which has density 0, after permutation, we can think about, once again, we can think about a set which has a density 0, and among its elements, there are elements which are untouched by our permutation. Yeah. So it's not a problem. There are some elements, I mean, these elements who are equal to 1 modulo 10, they were shrinked. So it cannot spoil the density 0. And we have also elements which were even numbers, but these elements, of course, they are spreaded, but we control the quotient of this spread. Yeah, it goes, let's say, 10 times above. Yeah, so it's not a problem to control them. So that's why this permutation preserves the density 0. But I'd like to present you also another example of the permutation which works like this. So it preserves density 0, but it does not preserve other density. But I will show you the example in which it's visible that it can spoil the density completely, because here the density was only changed. But I'd like to show the situation when the density is completely spoiled. Okay. So now, maybe this is visible. Okay. So now again, we divide natural numbers into sets, and we start these groups with powers of 2. So we have 1, then we have 2, 3, then we have 4, 6, 7, 8. Then we have no, it's something wrong here, sorry. I've forgotten about 5. So it should be 5, 6, 7, and the next group is starting from 8 maybe I will write the next group also. 10, 11, 12, 13, 14, 15, 4, 4, okay. And we start with 16, and then we go, next group is starting from 33, yeah? And we divide each group into the left and right part. They are equal to each other when we think about the cardinality. So I'm going to divide. So we have these main groups. Okay, let's do this like that. And then we divide them
checking,
into...
shouldn't the last number there be a 32? I mean, you always start the group with
Okay, you are
character.
right. It should be 32. Yeah. I need here the proper number of elements. So I need here 16 elements. So it should be like that. And I need divide by 2, yeah? So we have this left part and the right part. Left part is denoted with prime, and this right part with 2 primes here. And now we choose also something else here. So we choose the I don't know how to change the, maybe. Okay, I would like to change the color. Okay, so we would like to choose here even numbers from the left part. So this is even numbers from the left part. So it's 2, it's 4, it's 8 and 10, 16 and something else here. And the rest of this, the even numbers are denoted like that, K and prime. Yeah, so these are the rest of these groups. And now we have the, oh, maybe too many colors, it's not useful. Okay, so on the right parts, we have the same. So we choose for the set J and with 2 primes, also these numbers. Maybe I'm going to denote them like that. Yeah, so we have this one. And then from this second part of this also, and so on. Okay, so we have these families. And now I'd like to explain the definition of our permutation. So I'm going to transform only these even numbers within the group. So again, I'm not changing the situation between groups. I'm going to change only within this. So,
and that's always enough to preserve density, right?
Yeah.
Just to say, if you start off with something with density, this is going to preserve density.
Yeah. And I'm not going to change the order of these numbers. So I'm interchanging 8 with 12 and 10 with with 14. I think it's clear how it works. Okay, and now, okay, I will try maybe to show something else. Okay. So this is lemma which you guessed, yeah, that when we have this division and when we transformed only within these groups and we have the density 0 within these groups, then we have also the density is equivalent to having density generally. So this lemma shows that our permutation does not change the situation with the density 0. But now I'd like to define the set A. Maybe it will be visible here. Okay, let's do this like that. So for A, sorry for these technical problems, but sometimes not so easy. Okay. For set A, I'm going to choose here even numbers from the left part. Yeah. And odd numbers from the right part. So I'm taking for A. Even numbers from the left part, it's this one. Even number from the left part. And here we have odd numbers from the right part. So I'm choosing this one. And here I'm choosing this and that. And so on, yeah. So after this permutation, do you remember I've interchanged only this odd even numbers. So these even numbers from the left part, I transported to the right part. So after the permutation, I have here only these right parts. So after the permutation, I have this. Yeah, because I've transported these numbers here. So the same is there and so on. So we have the following situation. We have a set which had a, or maybe it should be visible still. Okay, I'm going to tell you. So here we had a set A, which had a density half, but after transporting this into these green parts, light green parts, we can see that the lower density of these parts is equal to 1/3 and the upper one is equal to a half. So we spoiled the density. Yeah? So not even we didn't preserve the density, but also we spoiled it. Okay. So I think we can come back to our attempt. I mean, to the situation when we wanted to find the characterization of these permutations. And what about this characterization? Okay. So we have to click this part. Okay. So in functional analysis, so-called Levy group is considered. It's defined as follows. So we have here the limit when we consider the situation on intervals, initial intervals which are longer and longer. But when we look at this carefully, it's not a density of the given set because the set which is testing, it depends on n. So we are checking the set of those n who after the permutation goes further than n on the interval from 1 to n. So those who were, let's say, jumped over n. So that's the definition which is used in functional analysis for this. And Obata showed in this paper that this is exactly the group G, which was considered previously. And we can find also another characterization of this group in the paper by Blumlinger, or Blumlinger, I don't know how to pronounce it properly. Sorry if I changed this name. So we have here the following description. For any subset of n, when we consider the difference between the cardinality of the set A on the initial interval to n, and the cardinality of this transported set on the same interval, in comparison with this interval, it goes to 0. So it's the same group. And when we worked on this topic, unfortunately, we were unaware of the beautiful work by Slezak and Zeman. We don't know how it happened, but it happens. Yeah, that sometimes we missed something. So we missed this result, which shows that this group can be described in the following way. So these are those permutations for which the statistical limit of P of n over n is equal to 1. So it's the limit in the sense of the ideal of sets of asymptotic density equal to 0. So it means, this description, it means that when we think about those terms of this sequence, which differs from 1 more than epsilon, we always receive the density of this set equal to 0 for any epsilon. So maybe repeating once again, for any epsilon, when I consider the set of P of those n, for which P of n over n differs from 1 more than epsilon, the density of this set is equal to 0. And this result, to be honest, is very similar to this one we obtained in Łódź. So we thought about the following sets. The sets of those n, okay, we fix the permutation and we fix a number greater than 1. And we try to control jumps caused by the permutation. So we consider those n for which the permutation of n in comparison, the result of permutation p on the number n in comparison with the initial n gives something proportionally bigger than a, and in an opposite direction when this quotient is smaller than a. And we receive the following, we consider the union of these two sets, and we receive the following result, which is almost the same, another kind of formulation, but it's the same as here. So it's nothing new, but that's our that's the result of our consideration. But it has something inside. Maybe that's something, the most interesting part of this talk about our results, because we receive something like that. So that's the result which we have already, yeah, which I showed you already. And then we receive the following characterization of this permutation, which preserves density 0. So we managed to describe this family using the idea of this set Z pi I, let's say, yeah, in the following way. I have time, so I'm going to show you this proof of that, but I'd like to finish with some questions. But still we are not able to describe the family S of D. So we would like to find here something, yeah? But we know that the family G is a subset of this family, and that's the subset of the family S of D0. So we are looking for the condition here, which is somewhere between these two conditions. So here we know that these sets have density 0. Here we know that the upper density of this one of these sets goes to 0, but we would like to have something between. We thought about conditions connected with controlling the speed of going to 0 with these densities. But we don't know the answer for this. So that's the idea behind it. That's our problem, let's say, yeah, to find something between these two parts. And this proof is quite easy. I'd like to present it here. Okay, so I don't know how to show you this this formulation, but it's written here, the formulation of our task. So maybe I can read this, that the family S of D0 is the family consisting of those automorphisms for which the limit of upper densities of the Z bar family is equal to 0. So I'm going to use the following simple lemma. When we consider subsets of natural numbers, and we know that the upper density of one set is smaller than gamma divided by 2, then when we subtract this set from the set of having the upper density equal to gamma, we receive the set with the upper density greater or equal to a half of gamma. Yeah, so that's obvious property. And now we'd like to show this equation, this equality. So let's start with this, that we assume that we have this limit, and assume that we have the set which does not belong to our family. So after the permutation, the 0 density is spoiled. And let's assume that the upper density of this set is equal to some positive eta. We denoted it by eta. So by the assumption that it goes to 0, we know that there exists the number A such that this density can be smaller than eta divided by 2. And then using this remark, we receive that the upper density of this difference is greater or equal than eta divided by 2. And by the definition of our set, we can observe that the following cardinality is not greater than A crossed with A intersection with this initial interval from 1 to an A. And this is an easy justification of this. So we just take a number from here, and looking at the definition, we received finally that it really belongs to this set. So this inequalities between cardinalities goes from the inclusion between sets. Yeah. Okay, so now when we have this, we can divide them by an A, and we receive the following inequalities. It works for any n, so we receive the following inequality, which is impossible because we assume that the density of the set A is equal to 0. So we have a contradiction. And then there is a proof of this in the opposite way. I mean, we assume that we have a permutation which has like that, and we assume that our condition is spoiled. So we have this upper limit of upper density of this set is positive. And now, since we can work here with monotonicity, we receive that this can be greater or equal to eta for any A. And now we choose an A such that we have on these intervals this inequality fulfilled for number greater than, okay, it's written here. If we have A greater than A prime, we have this inequality. So we choose further and further these numbers, yeah? And then we define set 0 as a union of those sets. So that's our candidate to show that there is a contradiction. And again, for a fixed A, we have the following inequality, which comes from this and from the definition of Z. And of course, from this, we receive that the upper density should be greater or equal than eta divided by 2. And then again, by the definition of this set, we have an inequalities between cardinalities of these sets. Again, justification is just by taking number from this set and justifying by definition that it gives something belonging to this one. So dividing by an, we receive the following inequality. And it means that we have the upper density of this set smaller or equal of 1 over A. But by the definition of Z, we can see that for any A, we can choose an A such that for numbers greater than an A, if we are in the set Z, then we are in a set from this part, yeah, here. So we have a density of this inverse image of Z with respect to this permutation equal to 0. So we have a contradiction because we can see that the density of this pre-image of Z is not preserved here. So it was a kind of it's a contradiction. So we have this characterization. And to finish, I'd like to show you also some ideas connected with another type of density, which can go with our. Okay, let's change this into that. I'll take a new piece of paper. Okay, so I'd like to say a few words about the density which was introduced by Polya. The definition, or maybe not in red. The definition is like that. We take a subset of natural numbers and we compute the following limit. We have the limit when theta tends to 1 of the upper limits when n tends to plus infinity of the cardinality of A on the interval. We control the proportion, yeah? One minus theta multiplied by n the length of this interval is here. Yeah, maybe it's not written properly. Of course, and it's called maximal density. Let's call it maximal density. I'm not going to write the definition of the minimal density because it's similar. Yeah, it's only difference is here the lower limit. But it can be characterized in the following way: that maybe the minimal density of A is the supremum of densities of subsets of A. So we choose subsets which possess the usual density, and we find the supremum of these densities. And the maximum density in a similar way, but taking the infimum of densities of the sets which contains our sets. So we have here density of those sets which contains A. And it's nice because we can show the description of the permutations which preserves asymptotic density in the following way. So let's write maybe the function. Let's say theorem f preserves, maybe not f pi preserves density if and only if for every A we have that the upper density of the image is smaller or equal to this maximum density of A. And it's also equivalent.
And this is observation of our colleague from Gdańsk, yes?
Again, you steal the show. Because I wanted to say that it's observation made by Jacek Tryba from Gdańsk. Okay, but okay, pi of A is greater or equal to this minimal density, and it comes from the fact that the function preserving asymptotic density, it not decrease minimal density, or on the other side, it does not increase maximal density. So it goes with something like that. So maybe I'd like Sebastian to ask, I'd like to ask you if you would want to add something. So this is the result of Jacek Tryba from Gdańsk in private communication with us. Sebastian, would you like to add something? Maybe I omitted something important.
Maybe I will add some small, but maybe quite easy, but maybe interesting observation, that if we have the permutation that preserves density in the way that Ulam expects, then those sets Z pi alpha have to has the polia lower density equal to 0. So it was one. It is quite easy observation. So those set cannot contain the set of positive density, but the permutation given by Coquette shows that this condition is not enough to be sure that the permutation preserves density. Yes, it is this only one-way condition.
Okay, so thank you for this comment. So I
Yes.
think that's all
Yeah.
what we've prepared. So maybe I can stop sharing my screen, but I don't know how to do this. I'm lost. Something is okay. Maybe I will go here. I don't know, maybe there. It's not so easy to stop sharing the screen. Oh, it's here.
So first, let me thank you for a very nice talk. Are there questions or comments? Do you happen to know why Ulam is interested in this kind of question?
No.
Not really.
No. No. No.
No,
No.
we don't.
Because I only knew it from Lazy's book on functional analysis, and I hadn't even realized that this was part of Ulam's famous Scottish problem book.
I'm afraid you have still some issues with your microphone. Maybe you will take it closer to your mouth or something.
We don't know even the price which was given by Ulam for this one. Because usually in the Scottish book there are prices for solving problems, but since we haven't got a solution, we are not so interested in the price. So
Also very difficult to collect together.
Mhm.
Questions or comments?
Well, is it clear what an answer would be? I mean, do you have a did Ulam give a clear criteria for what would amount to an answer? Because in mathematics, you can always sort of return the question and claim that that's the answer. You know, a set with property A, describe it. So it's the set with property A, right? So
Of course,
what would
yes.
amount as an answer that would have satisfied Ulam? Does anyone know?
I think that every condition that doesn't contain the word density would be appreciated. Yes.
Sure, but your conditions do involve.
Yes, of course. Yes, of course.
Interesting how much there is to still understand about different densities.
You're really not audible now. Maybe try again.
I'm here.
So, okay.
Now it's here.
Mm.
You were very audible for a minute. Now you're not audible at all.
Horrible now.
Just a few.
So, let me thank our speakers again. Oh, even my video. So
Thank you very much.
the video.
Very interesting.
So thank you.
Many thanks.
Thanks.
I'd
a lot.
like to ask for the permission. Can we join you sometimes to this seminar? I mean,
Always, yes.
okay, so thanks.
Oh, Mel, but this is the last seminar for this year.
No,
Is
next
it
week.
correct?
There's one next week.
Oh, sorry. Okay, sorry.
And then from Christmas or Hanukkah until after the AMS meeting in January. So there's a talk next week. And then we start again in the middle of January.
Perfect.
So thank you very much.
Thank you. Goodbye all.
See you.
Bye.
Bye-bye.